Hi, this is Tim, and welcome to the Math League YouTube channel. Today's problem comes from test number 12103, and it's the target test. Remember, 12103 is a high school test. This is going to be question number 6. Now, remember, question number 6 is usually about the second hardest problem on an 8-question target round. So what we have here is a request to compute the following infinite sum. All right, so anytime I'm looking at an infinite sum, the first thing I'm thinking is, wouldn't it be lovely if this was a geometric series, right? We love geometric series because there's an easy formula to compute the sum of all infinite number of terms. So let's take a look at that. Keep that in mind, okay? Let's take a look at what we have here. First off, we have a 2 to the n plus 1 in the denominator. That means the denominator is going to be multiplied by 2 every time n increases by 1. That's exactly what we want. That's what a geometric series does. The only problem is the numerator is not a geometric series, right? It's got cosine of something. And that thing inside the cosine is we're basically going to be adding pi over 3 each time. So we don't have what we're looking for in the numerator yet. But what we do have is something that will help us in terms of a geometric series in the denominator. Now, before I proceed to show you my solution, I do want to point out that the solution that was distributed with this test uses a slightly different solution. Okay, so I'm going to show you a completely different solution that takes advantage of something called Euler's formula. All right, so Euler's formula is an interesting way to combine the exponential function with sine and cosine. It says that e to the power of ix equals cosine x plus I sine of x. Now, the reason that that's useful is because, remember, we were looking to make this numerator turn into something that is geometric. Cosine of n pi over 3 is not geometric, but if I have e to the something involving n, that becomes a geometric series, and then we can use our sum of a geometric series formula. So check this out. Using the formula we have, what I want to do is take that x in Euler's formula and apply the argument that we have here in the numerator. Okay, so let me just write that down real quick. E to the I times n pi over 3, that's going to equal cosine of n pi over 3 plus I times the sine of n pi over 3. Okay, so basically what we can do is we can say that the sum from n equals 0 to infinity of e to the I n pi over 3 divided by 2 to the n plus 1, that's going to equal the sum from n equals 0 to infinity of the right-hand side of this equation above divided by 2 to the n plus 1. The thing is, because we're adding two things, I can actually split it out into two different sums. All right, so on the one hand, I've got the cosine of n pi over 3 divided by 2 to the n plus 1 plus I times, and I can pull the I out in front of the summation because it does not have anything to do with the n. So I can factor it like this: sine of n pi over 3 divided by 2 to the n plus 1. And what I want you to notice is that the thing that we have on the right-hand side consists of two pieces, right? We have a real piece over here, right? When you sum this thing here, it's all real numbers. In fact, when you take the second sum, it's all real numbers as well, but then it gets multiplied by I in the end. All right. So ultimately, the answer that you get to this thing on the left, which, remember, we designed this thing on the left so it would become a geometric series. The answer that we get to that thing is going to end up being a complex number. It's going to have a real part here and an imaginary part over here. The answer we're looking for problem number 6 is just the real part. So what I want to do is calculate the real part of the sum from n equals 0 to infinity of e to the I n pi over 3 divided by 2 to the n plus 1. Okay, so I'm going to calculate the sum, and then I'm going to just extract the real part, and that will be the answer, right? So what I have here is going to be the answer to the problem once I've done the calculation. Now, let's do the calculation. All right, so infinite geometric series, you know how that works, right? We need the first term. So the first term is, the series starts at n equals 0. So I'm going to need to plug in n equals 0 to this. E to the 0 is what the numerator looks like. That's just a 1. And then the denominator is 2 to the 0 plus 1, 2 to the 1, which is 2. Our first term is 1/2. Now, what about the ratio? Well, each time I increase n by 1, the numerator gets multiplied by e to the I pi over 3, and the denominator gets multiplied by 2. All right, so there we have what we need. Okay, we've got the first term, we've got the common ratio, and we're ready to set up our infinite geometric series. So the sum, again, I am looking for the real part of this. That's going to be a, which is 1/2, over 1 minus the ratio, which is e to the I pi over 3 divided by 2. I should probably put parentheses around this. We're taking the real part of the whole thing. And we don't want to stop early, right? We have to get this thing all the way to an actual complex number. Then we just ignore the imaginary part. All right. So first thing I want to do is let's just go ahead and multiply the top and the bottom by 2. So we get something that looks like this, just clearing out the fractions. Well, clearing out one layer of fractions, I should say. All right, now e to the I pi over 3, we can actually extract that portion of it. Remember, e to the I x is equal to cosine x plus I sine x. So what I'm going to have in place of e to the I pi over 3 is going to be cosine of pi over 3 plus I times the sine of pi over 3. And that is going to equal cosine of pi over 3. Remember, pi over 3 is 60 degrees. And so that's going to be 1/2 plus I. The sine of pi over 3 then is root 3 over 2. So I can replace that down here. I've got now the real part again of 1 over, starting with our 2, and we're going to subtract e to the I pi over 3, which we found is this complex number. So I'm going to subtract 1/2, and then I'm also going to subtract I times root 3 over 2. All right. Once again, I'm going to multiply the top and the bottom by 2 because I like to have only one layer of fractions if I can possibly have that happen. So the top is going to be a 2. At the bottom, we're going to get a 4 minus 1 minus I root 3. Okay, so I'm looking again for the real part of 2 over 3 minus I root 3. This is not yet a standard complex number, right? It's got the I in the denominator, so I'm going to rationalize the denominator. I actually don't care as much about the root 3. What I am concerned about is the I. I need to get the I out of the denominator. So what I'm going to do is multiply the top and the bottom by 3 plus I root 3. 3 plus I root 3. And what we have now is the real part of the top becomes 6 plus 2I root 3. The bottom becomes 3 squared, which is 9, minus I root 3 squared. I squared is -1. Root 3 squared is 3. So that's -1 times 3, -3. I am subtracting a -3. So I'm basically adding 3. All right, at this point, I can simplify this, right? The real portion of the numerator, 6, and the denominator is 12. So that's going to be a 1/2. And then the real portion, the imaginary portion of the numerator is 2 root 3, and the denominator is 12. The 2 and the 12 are going to cancel to give us a 1 over 6. So that's I times root 3 over 6. And we just want the real part of that. So the function real of this thing is basically, hey, let's just take the real part and ignore the imaginary part. And we are left with 1/2. Hi, everybody. This is Tim. Hope you're enjoying our videos. If so, you know what to do. Like, subscribe, turn on notifications, all that sort of thing. But what I'd really want to invite you to do is to send us an email at media@mathleague.org. Tell us which problems you'd like to see us cover next in our video series. Take care and see you in the next video.